Hey, Chongming.
Hey.
Can I just share my screen now
Yeah,
and put
please.
it on?
Yeah. I think the live stream has started. So it's good that stop.
Okay.
Right, great. Let's just wait for 2 more minutes.
Okay, thank you.
Hey, I think we should get started. So let me introduce our speaker. So today we are very happy to have Dr. Jianhao Zhang visiting us remotely from Penn State University. Jianhao got his PhD at Tsinghua University, then he spent 2 years in Hong Kong, and then now he's a postdoc at Penn State University, and Jianhao has been working on various aspects of the physics of symmetry-protected topological phases, including those protected by all kinds of symmetry, especially crystalline symmetry. And now he has marched on to this very interesting new direction that is symmetry-protected topological phase when the symmetry is only realized in the average sense. We encounter those in disorder system or in some kind of NCU setup. So without further ado, Jianhao, please take it away.
Well, thank you, Chongming, for your very generous introduction. And it's my great pleasure to be here virtually. Yeah. Today, I'm going to talk about our recent progresses on the average symmetry-protected topological phases with 2 settings. The first one is a disorder system, and the second one is a decohered system. And the most exciting discovery of our research is the intrinsically mixed topological state that do not have any clit limit. Yeah, the title here is studied from an Italian movie, which is called The Good, the Bad, and the Ugly. Firstly, let me introduce my outstanding collaborators. They are Ruochen Ma and Chong Wang from Perimeter Institute, Zhen Bi from Penn State, Yang Chi from Fudan, and Meng Cheng from Yale University. Yeah, the phase of matter can be classified in terms of the entanglement structures. And there are 2 different classes. The first class is a Shortrange entangled state that can be prepared by the finite depth local circuit. The O1 here means that the depth is of order 1, which means that the depth is finite. And the other kind of phase of matter is so-called long-range entanglement state. For example, for some topological order, for example, fractional quantum Hall state. And to prepare this kind of state, we need a quantum circuit that the depth of this circuit is of the order L as the length of the system size. Equivalently, in the thermodynamic limit, and the depth will be infinite. Yeah. A very specific kind of short-range entangled state is so-called symmetry-protected topological phases, which is studied very intensively during the past 2 decades. And the SPT phases are the gap state with unique ground state with short-range entanglement. And the SPT state is non-trivial if and only if the protecting symmetry is unbroken. Otherwise, it can be adiabatically connected to a product state if we don't care about any symmetry. That is atomic insulators. There are several very familiar examples. The first one is the Houdan chain. That is, every site we have a spin 1 degree freedom. At the open boundary, we have a dangling spin 1/2 degree freedom, which is gapless, and the whole bulk are gapped. And in 3 dimensions, we have free fermion topological insulators. Yeah, in topological insulator, we have a fully gapped bulk. And on the 2D surface, we have a Dirac fermion, which is gapless. Yeah. It seems everything
Can I ask a question? Can you hear us?
I beg your pardon?
I have a question. Can you hear us?
I can hear you.
Okay. So is there a way to quantitatively define range of entanglement?
We can if we have a ground state wave function, we can study the entanglement entropy of this state. The short-range entangled state should have whose entanglement entropy should be have an error law behavior.
Okay.
And the long-range entanglement may have several different behaviors. For example, for topological order state, we should have a topological entanglement entropy, which is a constant. Yeah.
So, but you're more specific about short-range entangle. In other words, so area law is what you mean by short-range entangle. Anything more than area law is long range. Is that how you're
for example, for some gapless state, we have a volume law. For example, we can have volume law, and and for 1D CFT, the entanglement entropy is of the order log L, or where L is the length of the system.
Right.
Okay.
Okay.
So can I go on?
Yeah.
Oh, thank you. It seems that everything would be great. So there is a natural question arise: why we bother the average symmetry? Yeah, the reason is that for the real physical system, you cannot make a system absolute isolate and decoupled from the environment. So the interaction and the influence of the environment on the physical system is pretty important. And the situations we focus on, the first one is the decoherence, and the second one is the disorder. Yeah, for real material, you cannot imagine that we can grow a single crystal without any defect or impurity. It's not possible in experimental setup. Yeah. For example, if we consider this kind of material, which is a topological crystalline insulator with a number 194 non-symmetric space group symmetry, and by RPAS experiment, a gapless fermion on the 010 surface is discovered. However, as I mentioned before, it is really hard to grow a perfect single crystal in the experimental setup. So as the RPAS experimental indicated, the gapless surface is pretty robust even for the symmetry on the average level. That is the crystalline system with imperfection. So it is worthy to study if the symmetry is average. What kind of phases can survive, and even another question: what kind of phases can appear that cannot be well defined in the clean system? Okay, let me show you another example. It's a 3D topological insulator with an average time reversal. How to achieve that average time reversal? We can consider that if we add a magnetic field, the time reversal symmetry is explicitly broken. Yeah, but if we consider a random magnetic field, and we have 50% that the magnetic field is in the one direction, and the another 50% have that the magnetic field in another direction. And very equivalently description is that we have a whole system, and half of the area have a up magnetic field, and another half should have a down magnetic field. Yeah. Experimental study shows that under the magnetic field, the surface of topological insulator will behave a quantum Hall state, which is quantized to 1/2 integer. Yeah. For example, if we have a positive magnetic field, it is quantized to n, which is integer plus 1/2. If it is a negative magnetic field, it's minus n minus 1/2. So if we consider there is a average time reversal symmetry, that is the area with positive magnetic field equals to the area of the negative magnetic field, the surface of the average topological insulator will be in the criticality of a plateau transition of a quantum Hall state. That is, the surface state of average topological insulator is still delocalized. Yeah. The non-triviality of the average total topological insulator is manifested by the delocalized surface state as a plateau transition of a quantum Hall state.
A quick question.
Yes.
Does the disorder matter? What if I had an antiparamagnet, so still half are up and half are down, but now they have a regular pattern instead of being disordered?
Oh yeah. If it is a antiferromagnetic order, it seems it is not work, because a antiferromagnetic is explicitly break the time reversal symmetry, because we can define a staggered order parameter. And this staggered order parameter breaks the time reversal symmetry explicitly. So right now, we cannot let the system in the ferromagnetic and antiferromagnetic.
But I guess, I mean, I'm not an expert in these things, but for a spin glass, you'd have a disordered. You might have a disordered, it would be a disordered situation, but there would be still some kind of order. Edward Anderson order parameter. So I guess I still wonder, why is it that they have to be placed randomly compared to an ordered pattern? Why is that essential? Can you hear me?
Oh, I can hear you, but not that clear.
Not that clear. I see. I'm looking the wrong way. I'm there.
I'm sorry.
Sorry. I guess I'm just pointing out that for a spin glass, there's still some kind of order.
Yeah.
Spin
And
glass does not break time reversal. There's no net magnetization.
No net magnetization, but antiferromagnetic, the only difference I'm seeing is the antiferromagnetic is an ordered pattern of the moments rather than a disordered pattern. Of moments.
Right, spin
But
glass.
still, net average is 0, right? So I just,
SOQ is not zero. I mean, if you go to different momentum component, there is pi pi is non-zero, m of pi pi is non-zero.
that's true.
So, if you don't want to have order, you don't want any m of any q to be non-zero. That's the case in spin glass.
Yeah, I wish I understood spin glass better to articulate my question. Maybe I'll let you go. I don't do.
Well, just maybe one quick comment. I think what he's emphasizing is just the average symmetry. Or any other proposal you may want to talk about, specific proposal about spin or whatnot, and the criteria.
So,
It
right,
does
so-
that preserve
so
it.
my question it's preserving the average symmetry, but maybe it preserves it in such a way that it's an ordered pattern versus a disordered pattern. That's my question.
The
Does
disorder
the-
pattern, naturally, you would say, well, there's an ensemble of different
Yeah.
orientation of.
They want to do some averaging over disorder configurations.
And if you
Yeah.
have-
There is only two for antiferromagnet.
In a real system, there's just one thing, right?
Right, so
But if I
if-
sell that,
Calculation, right?
so there's no averaging. Not an ensemble.
Yeah.
it's not an ensemble average in real system.
I think the confidence is that there's no guarantee a antiferromagnet will necessarily have a average time. Can have one that may actually have an effective average. Average, but it's not there.
It's not guaranteed because
Because you can definitely have an antiferromagnet that breaks power suspension.
Anti.
As I said, let me let you go. Thanks for all the comments. Continue, please.
So here's the outline of my today's talk. The first part is the average SPT phases, including the definition of average symmetry and the construction of average SPT ensemble, and several examples. And the second part of my today's talk is the very exciting part, that the intrinsic ASPT phases that do not have a click limit, including the classification paradigm with several examples. And the third part is the strange correlator as a diagnostic of the non-triviality of the ASPT phases. And finally, I will summarize my today's talk. Yeah. Before I talk about the average SPT, let me show you the definition of average symmetry by a very simple example. Let me consider a two-dimensional classical Ising model. Yeah, with a Hamiltonian like this. There are two different phases of the 2D classical Ising model. The first phase is a ferromagnetic phase, which is a Z2 spontaneous symmetry breaking phase. That is, the expectation value of the spin, Ising spin on each side is non-zero. And the other phase is a paramagnetic phase. Yeah, we call it symmetric phase. And this symmetric, this so-called symmetric is a Z2 average symmetric. What is that? Yeah, in the paramagnetic phase, we have a whole ensemble of states. If we pick up a specific state from this ensemble, this specific state is still Z2 symmetry breaking. But if we calculate, if we average over the whole ensemble, we will see that for the Ising spin on each side has a expectation value equals to 0, which we call this whole ensemble have a Z2 average symmetry. So the average symmetry in the is also called statistical symmetry. Yeah. In terms of density matrix, we have two kinds of symmetry. The first kind of symmetry is exact symmetry. The exact symmetry can be applied at the either side of the density matrix. For example, if we apply UK at the left-hand side of the row, and it will keep invariant up to a global phase. And so do the right-hand side. That is a exact symmetry. And the second kind of symmetry is a average symmetry. That is, we cannot individually apply the average symmetry operator in one side of the density matrix. That is, if we apply the UG as an average symmetry action operator at the left-hand side of the density matrix row, it will not, the row will no longer be invariant. And so do the right-hand side. But if we apply the average symmetry operator in both sides of the density matrix, and then the density matrix is invariant on this action. Yeah. And I'm sorry, here's some typo. Yeah, a short-range entangled density matrix or ensemble, it can be prepared by a finite depth quantum channel from a product state as this formula. Yeah. A very typical construction of the ASPD wave function in the clean system is a decoherent domain wall system construction. Yeah, if we consider a D plus 1D G symmetric SPT phase, a G and K SPT phase, sorry, here should be G tilde. And firstly, we consider let's see this picture. We have two domains of the G symmetry. And the right part is G1 and the blue part is G2. And in each domain, the G symmetry is explicitly broken. And the black curve is the domain wall of these two domains. Yeah, the second part is that we decorate a co-dimension P SPT, K symmetric SPT, which is another symmetry we consider. Yeah, and then right now we obtain a wave function that is K symmetric. What's wrong? That is K symmetric, but G symmetry breaking. In order to obtain a G symmetric state, we should find all possible G symmetry breaking patterns and quantum superpose them together to a single wave function. Let's see like that. And the superposed wave function is both K and G symmetric. That is the decoherent domain wall construction of the generic SPT wave function. Yeah. And for more details of the decoherent domain wall, let's see in this paper.
Slide is off on.
Beg pardon?
The slide is out of order. The slide, oh, yeah.
Oh, I'm sorry. Here's some problem, minor problem in my own monitor. Sorry. Let me give you a simple example that is a 1D cluster state. The Hamiltonian of the 1D cluster state have a ZXZ ZXZ configuration. And there is a Z2 cross Z2 symmetry of the 1D cluster state. And first Z2 is defined on the all sides, and the other Z2 symmetry is defined on the even sides. Yeah. And the ground state wave function of the 1D cluster state have a very clear decoherent domain wall picture that if we Zj minus 1 times Zg plus 1 equals to plus 1, and the Xj equals to plus 1, and if Zj minus 1, Zg plus 1 equals to minus 1, the Xj should equals to minus 1. That is, we decorated a minus 1 charge of X in the domain wall of Z on the even side. For example, if Z is on the all sides and X on the even side, we decorated a X charge at the domain wall of the Z. Yeah, and vice versa. Here's a very simple example of decorated domain wall picture. Yeah, there are more examples of decorated domain wall SPT states. The first one is a topological insulator with charge conservation and time reversal symmetry. It can be imagined like we decorate a integer quantum Hall state on each time reversal domain wall. And the second example is the 3D weak topological insulators with charge conservation and time reversal symmetry with a Z2 symmetry along the 2D translation. And this decorated domain wall pattern is that we decorated 2D TI on the translation domain wall along the Z direction. And the third example is the 2D. One second. Who write down something on the board? Oh, the third example is a 2+1D topological insulator with a Kim-Meili model, again with a charge conservation and a time reversal symmetry. The decoration pattern of this topological phase is we decorate a U1 charge on the 0D defect of time reversal. That is a time reversal domain wall junction, or a codimension 2 time reversal domain wall. Yeah. But now we discuss various decorated domain wall settings for various different kind of SPD phases with different kind of symmetries. Previously, we discussed the decorated domain wall in the clean cases. That is, we have an ensemble of G symmetry breaking patterns, and the final step of the wave function construction is proliferate the symmetry. That is, we should quantum superpose all possible decorated domain walls to proliferate G symmetry as an exact symmetry. That is the first case I write down in this page of slide. And the second example is a crystalline symmetry. If we consider a crystalline symmetry, the symmetry defects of crystalline symmetry is static. And also, all crystalline SPT phases can be considered as a decorated domain wall. That is, we can decorate some lower dimensional block states on all high symmetry phases, high symmetry lines, and high symmetry points. That is called defect networks, which is static for crystalline symmetry. And now for average symmetry, we still have an ensemble of G symmetry breaking patterns. But right now, we proliferate the G symmetry on an average level. That is, we no longer quantum superpose them together. We just put them to a unique ensemble, and the G symmetry, local G symmetry action will transfer a state in the ensemble to another state still in the ensemble. So for each quantum state, it is G symmetry breaking, but the whole we call the whole ensemble is G average symmetric. Oh, hey, I'm sorry. Maybe there is someone in the room that's damaged everything.
Disable annotation.
Is anyone damaged the things?
We are trying to disable annotation and kick out representation.
What's wrong? There is something wrong on my monitor.
Somebody who shouldn't be here found the way to the Zoom and annotate it. So we're here. Give us a moment.
It's okay. It's okay. I just wonder what happened.
I think we had a troll, but they are removed already.
I'm sorry for this.
We removed someone there, so we will do that. You option. Who's sharing this one? Is it on this computer? This computer?
Yeah, but I can.
I'm sorry for the very bad
It's not your fault.
experience.
Never seen this.
How could you just stop sharing and then share probably that there?
Let me stop and share again.
Yeah, you stop sharing and then, and bring it back.
Okay.
All right.
All right.
We can
Can you
block
guys
annotation.
see me again?
We can block annotation. We can also block them.
Sorry about that. Well, let me repeat what I said after the monitor has been destroyed. Yeah. Let me start by this slide. Yeah, for different kind of SPT phases with different kinds of symmetry, we have various kinds of decoherent domain walls. As previously I've discussed the internal SPT, that is we have so many different kinds of G symmetry breaking patterns, and we decorate some K symmetric states on the domain walls. For each state here, the state is K symmetric and G symmetry breaking. The things we have to do is to proliferate the G symmetry. That is we can quantum superimpose all these kind of G symmetry breaking patterns and to a single wave function. And right now, because this single wave function includes all possible G symmetry breaking patterns, if we can achieve that, these single wave function should be G symmetric as well. So if we can do that, this single wave function is the SPT state for both G, K, and G symmetry. And the second class of the symmetry is a crystalline symmetry. As we know, the defects of crystalline symmetry is static. That is high symmetry point, high symmetry line, and high symmetry faces. And the decoherent domain wall is also applicable to the crystalline SPTs. What is that? We decorate some lower dimensional states on the high symmetry points, faces, and lines, and do not do anything because they should be static. That is the decoherent domain wall pattern of the crystalline symmetry. Right now, in this talk, we focus on the average SPT. So, similar to the previous discussions, we still have several G symmetry breaking patterns as an ensemble of states. Okay, for each quantum state, it's still G symmetry breaking. And we try to proliferate the G symmetry to an average symmetry of an ensemble. The things we have to do is no longer quantum superpose them together. We just put them to a single ensemble. That is some kind of classical superposition. Yeah, that is, if we consider local G transformation, it will transform a specific G symmetry breaking pattern to another G symmetry breaking pattern. Right now, we have an ensemble of states, and both of these states are in the ensemble. So, although each individual state in the ensemble is G symmetry breaking, we call the whole ensemble is a G average symmetric ensemble. That is the average SPT, the decoherent domain wall pattern of the average SPT. Yeah. Let me emphasize a very simple example in 2D, where the exact symmetry is the SO3 symmetry and the average symmetry is the Ising average symmetry. And specifically, we consider a Haldane chain decoration on the Ising domain wall. The classification of this decoherent domain wall pattern is Z2, and the topological action of this decoherent domain wall is strictly be written down. And here A is a background gauge field of Z2 symmetry, and the W2 to the SO3 is a topological action of the Haldane chain. according to this topological action, we can see very clear that we decorate a Haldane chain on the domain wall of the Ising symmetry, and so do this picture. Let me right now. Let me think about the open system. That is a system with an open boundary. Here, as the shadowed region and the blank region are two domains of the Ising degree freedom, and the broad black curve should be a decorated Haldane chain. At the intersection between the domain wall and the open boundary, on the edge, there is a non-local spin cyclic pairs. Yeah, it's essentially non-local if the domain wall in the block is long enough. So for a short-range entangled ensemble of states of the Haldane chain decoration pattern on the Ising domain wall, on the open boundary, we have a long-range entanglement that is come from the non-local spin cyclic pairs on the open boundary. That is the average anomaly. That is, we have a short-range entangled block and a long-range entangled boundary. So right now we can see the average anomaly, but a question is that the average anomaly is a bit subtle and pretty hard to be characterized, at least relatively to the clean case. The clean case, the 't Hooft anomaly is pretty simple to detect. So just like the single Dirac fermion, gapless Dirac fermion on the surface of the topological insulator. So a natural question arises: how to detect the non-triviality of the ASPT directly from the block to avoid this subtlety on the boundary of the average anomaly? Let's keep this question in mind, and I will answer this question in the third part of my today's talk. Okay. Let me summarize the average SPT with the simplest direct product group structure. And the classification of the ASPT with this simple direct product group structure should be the Kuhneth formula, and n equal to 0 for the decoherent settings. For example, we should say that if the system only have the average symmetry, we cannot have any non-trivial topological state. That is, the only non-trivial decorated domain wall can still be non-trivial when the symmetry G symmetry is average. For example, we have a Levengood state. The ground state wave function of the Levengood state should be the quantum superposition of Ising domain wall patterns, or with every Ising domain will have a minus sign. Yeah, that is a non-trivial Barry phase of the Ising domain wall deformation. But if we decohere the system, how can we define the Barry phase? Because we no longer have a Hamiltonian. We no longer have a single wave function. So we no longer have a well-defined Barry phase. So the non-triviality of the Levengood state will be disappeared in the decohered system. And even for the disordered system, the n equals to here n equals to 1 for disordered system. Let me emphasize why there is two different settings by an example. And the second character of this kind of ASPT is that every ASPT ensemble can be purified to a clean SPT wave function. And that is pretty simple, that because we have right now for ASPT, we have an ensemble of states. That is a classical superposition of the different decorated domain walls. The purification can be imagined that we just change the classical superposition to a quantum superposition. It can always be done for the direct product group structure. So two natural questions arise. The first question is that for the generic group structure, that is, the exact symmetry and the average symmetry have non-trivial extension. How to classify the ASPT in these kind of symmetric classes? And the second question is that, is there any ASPT density matrix or ensemble that cannot be purified to a clean SPT? Yeah, let me answer these two questions.
Sorry, before we move on, can I ask a simple question?
Okay.
Yeah, on this slide. So can you remind me what was the Kuhn formula without any average and symmetry? What does n start from? Or what does, I mean, what is there? One of them is just this. when n is
No. I'm sorry. Here should be P from n to d plus 1, and n equals to 1 for decoherence, and n equals 2 for disorder.
Wait, so this formula has typos. Wait,
Big part.
you're saying this formula on the slide has typos, and it should be changed?
Yeah. Sorry for the typos. Yeah. The physical meaning that the decoherence will destroy the Berry phase non-triviality of the average symmetry, and the disorder will destroy the 0D declaration of K charge. Yeah. Let me answer the previous two questions in my second part, and that is intrinsic ASPT phases. Yeah, previously I discussed the decohered domain wall patterns of the construction of SPD wave functions, but as I mentioned before, these kinds of procedures of decohered domain walls are not always be guaranteed to be achieved. There are so many consistency conditions of constructing the SPT state wave function. The first consistency condition is that all phases decorated on the G defects should be K-symmetric gapped state. Otherwise, if we decorate some gapless state, no matter what we do, we cannot obtain a gapped box state after the G symmetry proliferation. So it is the first consistency condition. And the second consistency condition is that if we decorate some K-symmetric states on the G defects and try to proliferate the G symmetry, that is, we quantum superpose all different kinds of G defect networks, the K charge should be well defined for all different decohered domain wall patterns. You can see in this picture here, each orange belt is the codimension 1 defect of the G symmetry, and each green dot should be the codimension 2 defect of the G symmetry. Yeah. In order to obtain an SPT wave function, we should quantum superpose all kinds of decohered domain walls. That's required that each decohered domain wall should have a well-defined K charge. Imagine if the left-hand side picture have a different and the right-hand picture have different K charges. What is the K charge of the psi SPT? It's unphysical. So if we want to have this kind of quantum superposition, we should first make sure that every state that we want to quantum superpose should have a well-defined K charge. And all of them should be equal. And the third consistency condition is the so-called Berry phase consistency. That is, firstly, if we deform the first pattern to the right-hand side pattern, these two patterns can have a different phase. According, this can be different by a U1 phase. But if we deform the G symmetry defect, go through a closer path and return to itself, the total phase acquired along the closer path should be canceled. Otherwise, we will have a multi-value wave function, which is non-physical. Yeah. Well, in order to have a single value wave function, the closer path of Berry phase should vanish. This is the Berry phase consistency condition. Yeah. Then the previous discussions are all focused on the clean system. For the system with decoherence, we no longer have a Hamiltonian. We no longer have a well-defined Berry phase. So the third Berry phase consistency condition will be abandoned. Yeah, for the disorder system, because of the Anderson localization, even the second consistency condition can also be abandoned. Let me emphasize why is that. For example, if we have if the K charge of the left-hand side figure is different from the right-hand side figure, yeah, let's say K1 and K2, let me deform the left-hand side to the right-hand side. The to consistent deform them, we should dope the system with K charge K2 minus K1 to compensate the K charge difference. But if we have a Anderson localization that is strong enough, we can localize the doped charges. And without the Anderson localization, the doped charge will propagate in the system as a plane wave and lead to the system to gapless state and with a long range correlations, you know. But if we have an Anderson localization, the doped charges are localized. They are still gapless, but the gapless excitation is localized. That is, all gapless excitations are local excitations and don't affect other parts of the system. So this deformation is also adiabatic with the Anderson localization. Let's consider, let's emphasize this fact by an example in the future. Yeah, so the classification data under decoherence, the ASPD classification is all classification data should be the E2 page of spectral sequence with the obstruction conditions. That is the mathematical descriptions of the all previous consistency conditions. And the last layer of the differentials, that is the Berry phase consistency conditions, will no longer important for the decoherent system because of there is no well-defined Berry phase in the decoherent system. And for the ASPD with a disorder, even more, less about one differential, which corresponding to the charge fluctuation, will be localized by the quenched disorder, and the corresponding differential in the spectral sequence is also no longer be important for the disorder system. Yeah. Right now we can see that we have the same ingredients for constructing SPD wave functions and ASPD ensembles. The only difference is that we have less consistency conditions for ASPD states. So we have a natural consequence arise. We have the same ingredients but less constraints. So when there may be some emergent new phases with loosened by the abandoned obstruction conditions. That is intrinsic ASPD states.
Yeah,
Hey.
quick question. So when you say ASPD with disorder, you're allowed to have a charge fluctuation. I guess that already implies that you have to think about a system without any charge compressibility.
Yeah, exactly.
Okay, so if I would like to put the story around and somehow have some disorder system with finite charge compressibility, then I do have to care about this. I cannot make this argument that I cannot.
Yeah. Right now we are considering a canonical ensemble. If we consider a grand canonical ensemble, all my arguments should not be applied.
No, but that's regardless of what ensemble you use, right? Charge compressibility is something that you can define independent of what ensemble you do.
Yes.
Okay.
Yeah. We call this kind of ASPD states that is loosened by the abandoned obstruction condition, intrinsic ASPD states. Yeah. As I said, there is no clear limit of this intrinsic ASPD state. So a natural question, what is the purified state of the intrinsic ASPD density matrix? Equivalently, how can we prepare this ASPD state from what kind of pure state? A conjecture of the purification is that a ground state of a gapless Hamiltonian. And let me emphasize this by an example. If we consider K symmetry equals Z2, which is exact, and the average symmetry Z2, and they have a non-trivial extension to the Z4 symmetry. And from the group cohomology classification, the Z2 symmetry cannot protect any non-trivial SPT phase. That is H upper 2 Z2 U1 equals to Z1. In the clear limit, we can define the symmetry generators of the Z2 symmetry, that is UG equals to this, and UA equals to this. We can easily prove that UG square equals to UA and UA square equals to 1. That is a Z4 group structure. Yeah. If we force a decoherent domain wall pattern by this projection operator P is 1 plus ZXZ over 2, and strictly impose the decoherent domain wall. With the imposition of decoherent domain wall, the UG will be deformed to a sigma JX times e to the I pi over 4 sum over J I minus sigma X times sigma X. That is that is no longer an on-site symmetry. Yeah, and UA equals to 1. So in the decoherent domain wall subspace, there the symmetry class should be the Z2 anomalous symmetry action, which is identical to the symmetry action of the edge state of Levengood state. So this Z4 gapless SPT has a Hamiltonian that is the Levengood edge Hamiltonian in the decoherent domain wall subspace. Yes. And based on this Z4 gapless SPT, we apply 2 quantum channels to this state. The first quantum channel is rho plus Z rho Z over 2. And the second quantum channel is rho plus X rho X over 2. And after these 2 quantum channels, we destroy all long-range correlations of the Levengood edge and obtain a well-defined decoherent domain wall patterns, which it should be a average cluster state again in the decoherent system. So we can say that we have a 1D Z4 gapless SPT under decoherence, and after we can use that to prepare a 1D average cluster state with a Z4 symmetry. Yeah. As Changwing asked, why we should abandon the 0D decoration in the system with Anderson localization? Yeah, let me emphasize that by a very simple example. We consider a system, a lattice free fermion system with U1 charge conservation and the lattice translation symmetry in the D-dimensional system. You know, for a D-dimensional system, we have a Z to the D translation symmetry. And we can just consider a very simple Hamiltonian, that is a tight binding Hamiltonian with a on-site chemical potential. For the chemical potential larger than 2T or less than minus 2T, the band is full fill or full empty. All of that are atomic insulator. And with intermediate T, the intermediate chemical potential, this should be gapless and long-range entanglement, that which is ensured by Lipschutz-Mattis theorem. For example, if we have an atomic insulator and we dope the system by some holes, and these holes will be a Bloch wave and propagate in the system, which lead to a long-range entanglement and gaplessness, right? But if we consider some disorders that breaks the exact translation symmetry to an average translation, by this disorder Hamiltonian, with you can see that this disorder is some random potential on the lattice sites, and how we restore the average symmetry of translation, we just make sure that the expectation value of this random potential epsilon j equals to 1, equals to 0. Yeah, in this strong disorder limit, you can see that all doped holes are localized by the random disorder potential. And right now, the intermediate state for the intermediate chemical potential is still gapless, but the gapless modes are all Anderson localized. So the intermediate state is gapless and the short-range entangled. So we can see that the atomic insulators with two different fillings can be interpolated by an adiabatic path. The adiabatic, but this adiabatic path is, we call this compressible interpolation, because every state on this adiabatic path is gapless but localized. So that is why we should abandon all these zero-dimensional decorations in the decoherence, disorder settings. I'm sorry. Let me emphasize the higher dimensional decoration.
I have a quick question, or maybe hopefully.
Yes.
Quick. I just want to make sure I have the right framework of what I'm thinking while you're giving your presentation. So at some point you were talking about open systems and density matrices, which had you had defined your average symmetry that way. And now you're talking in this Anderson localization picture. We could have a pure state.
In Anderson localization, we have an ensemble of states.
Symmetry?
Yeah, very good question. In the disorder system, we have a self-average. Yeah, because we have we can consider the whole system, very large system, is composed by different pieces, and the size of each piece should be the coherent length of the system. So, although the whole state is pure, if we consider this whole system as a pure state, the ensemble average is piece by piece. Yeah, we can slice the system to different pieces and go average over the different pieces.
Can I think of it as if I just take one region of the system and trace out the rest of the system, I'll end up with a density matrix which is similar in form to your previous density matrices?
Well, I don't think so, because why we should have a different rule of games for the disorder. We don't have a preferred basis. So if we do not have a preferred basis, consider we have a two-way functions psi1 and psi2, and the superposition psi1 plus psi2 is also well defined because we don't have a preferred basis. So in the ensemble, psi1, psi2, and psi1 plus psi2 should also be well defined. So that's why we require psi1, psi2 have the same K charge. But if we have a Anderson localization, we choose a preferred basis. That is a Hamiltonian of the Cringe disorder basis. We have psi1 corresponding to a specific disorder realization, and the psi2 corresponding to another disorder realization. Right now, the psi1 plus psi2 is unphysical because we don't know what is the superposition of different disorder realizations.
That's not what I was. That's not what I was referring to, though. I was just thinking you take the pure state and then you trace out the other. You can write the density matrix psi, ket psi, bra psi, and trace out the remaining system, and you have a subsystem which is described by a density matrix. Is that density matrix similar to the ones we were talking about in the earlier talk?
I don't think so. I don't think so. Sorry. Yeah, because if we slide the system to the different pieces, for each specific piece, the translation symmetry is explicitly broken. Yeah, the only what I mean about the average translation is that if we average over the random potential on each pieces, you can imagine different pieces of the whole system as an ensemble. The average over different pieces should restore the average symmetry. So if you choose a specific piece and trace over all other places, you will obtain a density matrix that explicitly break the translation symmetry.
Okay. So then what you're talking about is a density matrix I could think of as the ensemble of disorder realizations, the mixed state according to that. Is that
Yeah.
the right density matrix I should be thinking of?
Yeah.
Okay.
So can I go on?
Yeah.
Yeah, thank you. Let me emphasize a higher dimensional example, decoration example by some tedious mathematics. If someone don't care about the mathematics, please just abandon this slides. Sorry. Yeah, the symmetry class here is our exact symmetry is a Z2F fermion parity, and the average symmetry should be Z4 cross Z2 in 3+1D system. And a Majorana decoration is labeled by the 2 cocycle H upper 2 Z4 cross Z2 coefficient. And by some spectral sequence calculations, this data is obstructed because of the Berry phase inconsistency. That is, the last layer of obstruction condition is violated. But if we decohere this system, the last layer obstruction will be abandoned, and the system will be an intrinsic ASPT state. Yeah. And the classification of an ASPT phases with a generic symmetry group is still in the context of group cohomology. All ingredients of the spectral sequence should be the E2 page spectral sequence with a different obstruction conditions that can be formulated as differentials of the Atiyah-Hesburgh spectral sequence. And the difference is that because of the abandonness of the consistency condition, we should also abandon some differentials of the spectral sequence. And now the classification of the intrinsic ASPT phases are the generalized group cohomology with some modified differential formalisms. Okay. Yes. Previously, we remind a typical question in our minds that how can we detect the non-triviality of the ASPT phases directly from the block because of the subtlety of the average anomaly on the boundary. Yeah.
Sorry, Jiho.
Hey.
Just a quick reminder, we're at a 1 hour mark. So is it possible if you wrap up, let's say 5 minutes or so? 5 minutes?
A bigger pardon? I cannot hear you.
Oh, sorry. We're at the 1 hour mark. So is it possible for you to wrap up in 5 to 10 minutes?
Oh yeah, I can finish it in 10 minutes. Okay. Yeah. The bulk of ASPT, we have right now we consider let me just focus on the decoherence settings. Yeah, we have which is also applicable to the disorder settings, but let's see for simplicity. Yeah, for ASPT density matrix, and we choose a reference density matrix. It's a trivial density matrix. That is, we also have a ensemble of G symmetry breaking patterns. The only difference is that we leave the G domain wall empty, and then we try to proliferate the G symmetry to a classical ensemble, proliferate the symmetry, and towards a trivial ensemble of states. Sorry. And so we obtain the reference state is that we have the different G defect networks without any decorations. So it should be trivial. Yeah, with these two ingredients, we can define strange density matrix by as a non-Hermitian operator with this. In the cat space, we choose the states from the row ASPD, and in the bra space, we choose the states from the reference state. And with this strange density matrix, the strange correlator is defined as the expectation value of some local operators with respect to the strange density matrix. And we expect that the strange correlator would be either long range or polynomial decay if row ASPD is non-trivial. Let me emphasize this by a very simple example in 2D. The exact symmetry is Z2 cross Z2, and the average symmetry is Z2. And the decoration pattern is that we decorate the 1D cluster state on the domain wall of the Z2 average symmetry. The local Hilbert space can be constructed like this. At each side, we put an Ising degree freedom as a violet arrow in each green circle. Yeah. And on the bound, on each bound of the triangle lattice, we put 2 qubits. And for these 2 qubits away from the domain wall, we just put them together and polarize them to a +1 state and disentangle them with entire system. And on the domain wall, we just form all the qubits on the domain wall towards a 1+1D cluster state, which can be done because we have a Z2 cross Z2 exact symmetry. So the decoration pattern is explicitly formulated in this lattice model. Yeah. And the goal we to do is that the strange correlator of the exact degree freedom can be mapped to a classical 2D loop model. Yeah, here we formulate the K-strange correlator by the ingredients, where PD is a Boltzmann weight of the classical Ising model in the paramagnetic phase. For PD is and X is the product of X to the minus L, where L is the length of the domain wall, and where X equals to e to the minus 2 beta. Beta is the domain wall tension. That is the tension, the cost. We create a unit length of the domain wall. And the second ingredient is the wave function overlap between the cluster state and the product state in the trivial, which is trivial. That this is pretty important because it may renormalize the domain wall tension. And the third ingredient is that this formula is non-trivial. Only 2 points R and R prime are connected by a single domain wall. Yeah. As we say, naively, we have a Ising we have an Ising ensemble, right? So the corresponding loop model should be the O1 loop model, because there is only one possible loop in the Ising model, because which is the domain wall between the Ising spin up and the Ising spin down. So in the classical Ising model, the loop fugacity should be n equals to 1. But the things become different if we decorate something on the domain wall. This is because of the wave function overlap between the Z2 cross Z2 cluster state and a trivial state. And the right coefficient 2 is pretty important and universal, that after some calculations in the denominator of the K-strange correlator, we can find that the dominator of the K-string correlator is identical to the O2 loop model. And the universal 2, which is come from the wave function overlap of 1D states, renormalize the loop fugacity from the O1 loop model to a O2 loop model. Yeah. So we map the strange correlator of K to a loop correlation function of O2 loop model. Let me review the loop model, general properties of the loop model. Yeah, the partition function of O2 loop model is here. The X tilde is a renormalized loop tension, and the 2 to the N D is the loop fugacity, and where L is the total length of the domain wall, and N is the total number of the domain walls. And as we see before, the loop correlation function is that the probability that R and R prime are connected by a single domain wall, that is belongs to the same type. Yeah. In general, a loop correlation function of O1 loop model can be calculated explicitly. In this, here we can see that the RG phase diagram of O1 loop model, we have a right line which is dense loop phase, which is attractive fixed line. That is, in this phase, the system have so many loops, and the configurations of the degree of freedom is pretty mass. And the blue line should be a dilute criticality. That is a transition between the dense loop phase and the dilute loop phase. And you can see that if the loop tension is less than the blue line, the system will flow to the x-axis that's corresponding to there is no loop. That is, the system should be in the single whole domain. Yeah, in the dense loop phase and the dilute criticality, the loop correlation function have a critical behavior that is power law, and the critical exponent can be explicitly calculated by some loop guess techniques. Okay, and so for the range that x larger than square root 2, the K-string correlator have a power law behavior where the critical exponent delta 2 equals to 1 over 2. And you may see that there is another regime of the loop tension that is lying in the dilute loop phase of the O2 loop model. But don't be frustrated. We have another tool is that in this phase, we can measure the strange correlator of G degree of freedom. And in this region, originally, the loop tension corresponding to the dilute loop phase of the O1 loop model, but to the dense loop phase of the renormalized O2 loop model. So in this regime, we can measure the G strange correlator, and the G strange correlator is a constant. So the global phase diagram of the strange correlator is that when x larger than xc, we can measure the K strange correlator, which has a power law behavior, and for x larger than xc icing but less than xc loop, we can measure the G strange correlator, which is long range. So with these two kinds of strange correlators corresponding to K and G, we can unambiguously determine the rho ASPD and its non-triviality. Okay, let me summarize my today's talk. The first part, we define the ASPD phases in different settings in the disorder and the decoherence. And the second part is intrinsic ASPD phases that do not have a clean limit from obstructed or intrinsic gapless SPD states. And the third part is detecting the non-triviality of the ASPD phases directly from the block through the strange correlators. And specifically, the strange correlator can be mapped to a watermelon correlation function or loop correlation functions of ON loop model with a renormalized loop tensions and a loop fugacity in 2D. Okay, that's it. That's all my today's talk. Thanks for your attention.
Good, Jianhao. We had quite a few questions during the talk, but any last burning questions? No? Okay, I think, thank you again. So
Thank you.
really sorry for the Zoom bomb.
Oh, it's okay. It's okay.
Meredith, you can stop the